So what we've done so far with the governing equation is show how we can simplify it in certain cases. For example, if you're dealing with band layer flow or flow over slightly curved surfaces, the flow remains attached to the surface and doesn't separate. In that case, you can make certain simplification, in particular in 2-dimension, so that you end up with equations that are much easier to understand and analyze. We started showing how they can be expressed in a dimensional or non-dimensional form. And then we discuss how this equation can help us understand how a certain flow variable, such as U, is dependent on other flow variables, such as pressure and velocity, as well as the Reynolds number. So once we have that, we'll be able to derive useful information. But before I do that, I'm going to take a step back to try to provide some context. And I'm going to switch to this tablet. So we're looking here at perhaps a problem which involves a slightly curved surface with the fluid flowing from the left. Formation of boundary layer, as usual, is appearing, and we know that it varies as a function of x, so as you travel around the surface. So if we're trying to, as an engineer, understand how perhaps the coefficient of friction at this point is going to depend on flow variables, you need to first understand what the coefficient means. And in fact, in this case, it's the local coefficient of friction. So that is, it's the local shear stress at the wall divided by half of rho V infinite squared. And in order to get this value, you would have to essentially characterize what the shear stress is. It's the dynamic viscosity multiplied by du over dy, calculated at the wall, that is at y equals 0, and you divide that by half of rho V infinite squared. So let's assume you are the engineer and you want to know for a given surface how that CF is going to change as a function perhaps of velocity or the density or the viscosity of the fluid. Well, you can carry out one experiment or you can rely on correlations that would have been derived previously by other researchers. So the question is, what experiments should be run? Do you vary velocity, do you vary density, viscosity, and so on of the fluid in order to see and understand how CF depends on this variable, or can you work with a subset of variables? And that's where we use dimensional analysis, or we refer to the governing equation. So let's try to understand that. CF, we will see later on, is actually a function of the Reynolds number. First, it's a non-dimensional quantity, and therefore it should be a function of all the non-dimensional quantity. We're going to use the position x as a characteristic length, but it is also a function of dp infinite over dx, that is the rate of change in pressure as you move along the surface. So where does that come from? If you have a flat surface and the fluid flows over it, then in that case we know that dp over dx is 0. There is a 0 pressure gradient along. The pressure gradient builds up as a result of the interaction of the flow with the surface. So if you've got particles heating the surface, then you have what is called stagnation, a high pressure region. All the energy goes into creating a high pressure. And then as you go along and the fluid accelerates to go around the obstacle, the pressure decreases. So in that case, you would have a dp over dx, which is negative. The other thing we found from our derivations of the equations is that the pressure doesn't actually change with respect to y in the boundary layer. That is, dp over dy is equal to 0. Therefore, the pressure outside of the boundary layer is the same as the pressure inside the boundary layer. Okay, so that's why we're only interested, in fact, in how the pressure outside the boundary layer here changes with respect to x. That quantity is non-zero when you have a curved surface, and depending on the curvature, you have different values. So clearly, the coefficient of friction is going to also be dependent on the wet pressure changes. And that effectively, that quantity reflects the shape. The shape is going to have an impact on the coefficient of friction. So it's an important fact. But there is a way of taking it out of the relationship. If you decide that you're going to derive a correlation, which tells us how this quantity varies as a function of this one, and potentially this one, why not choose in your experiment a shape that's always going to be the same? If you're interested in coefficient of friction over the cylinder, you could decide that you're going to experiment only on cylinder. So all the experiments you're going to do is going to build in a relationship between CF and dp and RE, but the dp is going to always have the same influence. So for example, if your experiments tells you at the end that you have something like 2.1 Reynolds number to the power of 1.2, and then dp over dx infinite of 1.1, let's say, just pick a relationship at random, you could easily say that because it's always the same shape, it turns out that this quantity can be built into this one because it's always going to be the same gradient. Now, this one I should have said should have been expressed as a non-dimensional quantity because each one of these terms are non-dimensional. So this should be the non-dimensional quantity. So we can build that into a coefficient, and the coefficient will capture both of them, and we don't need to resolve that. Same, if you're studying only flat surfaces, you can just say that that correlation you derive only apply to flat surfaces. Therefore, you don't need to show the relationship between CF and dp over dx. So that's the point I wanted to make, 2 points. First, the dp over dx is the complicated one. Second, we need to be able to tell the experimentalist who is going to derive such a function from experiments, what are the important variables that he needs to test. That is, in order to find that relationship, he's going to have to vary all the variables that influence this quantity by certain increments, measure the coefficient of friction, and try to fit such a relationship to the data that he gets. So minimize the scatter or minimize the error between the approximation and the scatter of points that he got from the experiments. That's the purpose of trying to carry out the experimental campaign in order to get a set of correlations. If you look at the information provided to you on the loop side, on the assessment tile, if you go to formula, you will see, for example, that you have correlations for the coefficient of friction, and you see that it's only a function of Reynolds number. If you look at Nusselt number, it's only a function of Reynolds number and Prandtl number, and so on. There are other things like that. So that's what I was discussing there, is how do we actually find that out? How did we know that it was only going to be a function of Reynolds number? So that's the next step. And in order to do that, I'm going to switch back to the PowerPoint. So we move to the next slide. Okay, so what we have here is velocity is a function of variables that, as an engineer, you intuitively can think are going to have an impact. So the velocity is going to vary as a function of position along the curved surface, position away from the wall, the actual length of that surface, the free stream velocity, the fluid properties, and then the shape of that surface, so dp over dx. Now, you know the relationship between the shear stress and the velocity. It's mu times du over dy at y equals 0. So that derivative with respect to y, and then you assign a value of y equals 0, removes the dependence on y, and that's about it. That's the only difference between these two, and it comes from this definition of the shear stress. So we know that if you were to characterize shear stress, you'd have to carry out experiments varying x, L, V, rho, U, dp over dx, perhaps 10 times this one, 10 times this one for each one of these, and then 10 times this one for each one of these combinations, and so on. It becomes completely impractical. And that is why you shift to non-dimensional equation. Now, when I said that I intuitively thought these were the important quantities, you can also find that out through the equations. So if we go back to the dimensional form of the equations, we see that u is going to be a function of v, p, or dp over dx, mu, the position y, and the position x, as well as density. Just look at the equation, and you see by these two what are the important variables. That's one way of doing it. Then if you go to the non-dimensional form, u is going to be a function of non-dimensional x and y and pressure gradient and Reynolds number. Okay, so if we go back to the next, we see that we went from that to there, x, y, Reynolds number, and dp over dx. The velocity, capital V, the length, L, the density, the viscosity, all fit into the Reynolds number. And that's why suddenly we're dropping significantly the number of variables that U depends on. If we now look at the coefficient of friction, which is a non-dimensional form of the shear stress of the wall, you use this, that drops the dependence on Y, then you calculate CF, and you end up with essentially CF being equal to du over dy multiplied by 2 divided by the Reynolds number. You evaluate this at y equals 0. That's what removes the y dependence. And we end up with, and I don't go through the details, you will find them in the lecture notes, with these important results. The coefficient of friction at a location x, so if you don't have the overbar, it means local. Sometimes you will see the x and sometimes not. You have an equivalent, which is 2 divided by the Reynolds number. Again, x is the characteristic length. And we said that it's dependent of a function of x star and Reynolds number. If it's the average, it's going to be dependent on the Reynolds number only. So, and you divide by the Reynolds number. And that agrees with what we saw here. Coefficient of friction is a function of the Reynolds number. So the X has actually disappeared. It's been put into the Reynolds number, it turns out. Okay. So we have these important results. It's important because it tells the experimentalist that if he or she wants to characterize the dependence of CF on flow variables, he or she only needs to vary X number of times and vary the Reynolds number. Because the Reynolds number is going to be calculated using X as a characteristic length, they are both fitted into a single non-dimensional number. So let's move on to the next one, which is the thermal boundary layer. You can apply the same reasoning. You can look at your governing equations, see all the variables that will influence temperature. You can then move to H by using the definition of H, which means the derivative with respect to Y, and then you calculate that at a certain value of Y. So Y is no longer variable, it's fixed, Y is 0. So it disappears from the functional description. The only difference is that Y is gone as you move from there to there. If you look at a non-dimensional equation, we have X star, Y star, Reynolds, Prandtl, and dp over dx. If you decide that the correlation that you're going to apply, that is how you're going to define F3, will relate to experiments with a single shape, then the influence of dp over dx is not gone, but you can fit it into the coefficient. That is, if we look back again at these correlations, we have different correlations for, so it's Nusselt now, for the flat plate and for the cylinder. The coefficients that we see here and here are not the same. Okay, so that essentially is the change in the dp over dx that informs that change in coefficients. It's essentially subsumed into the definition of F3. So now we have a Nusselt number, which is going to be a function of all that. If the Reynolds number is expressed using X as a characteristic length, these two can be combined into one. And so you'll just have the Reynolds number and the Prandtl number. When you average over X, the X disappears as well, and you just have a dependence on Reynolds number and Prandtl number. Does that agree with the correlations we have? For the flat plate, yes, Reynolds, Prandtl. For the cylinder, Reynolds, Prandtl, yes, and that's the justification for that. For the mass transfer or the mass, the concentration boundary layer, it's a similar concept. We also have a mass transfer coefficient, so it's very similar in derivation as what we looked at early on, but we don't have the Nusselt number. Instead, we have something called the Sherwood number, and the Sherwood number is a non-dimensional form of the mass transfer coefficient H. It's non-dimensionalized by multiplying by the length and divided by the diffusivity coefficient. So we have Sherwood now is a function of these. So instead of Prandtl number, we have the Schmidt number is the characteristic of the non-dimensional quantity of importance, and we've seen that before. Okay, so we just have essentially a general explanation for the shape of the correlations that are used.